right, it'll be fun. Welcome, everyone. My name's Mark Hughes, and I'm here on behalf of our sponsor companies, all about AdvancedAssembly.com and RoyalCircuits.com. We are here to answer any and all questions that you have. And as an added bonus, some of those will even be right answers. I know. Who knew? Who knew? So
very optimistic.
If you have any questions following this webinar, feel free to shoot us emails at sales@royalcircuits.com or sales@advancedAssembly.com, and we can answer them. You can also email me directly, mhughes@aapcb.com. This webinar will be posted within 2 business days at aapcb.com/blog and royalcircuits.com/blog. With that, let's go ahead and get going, and let's get to know our presenters. I should mention, though, at the bottom of your screen is the question and answer box. Let's see if I can get that animation to come up. There's a question and answer box. Please ask all of your questions there. I won't be monitoring the chat. All right, let's get going. Elijah Gracia is a process engineer with Royal Circuits Solutions. Elijah, tell us a little bit about yourself and what you do, buddy.
Hey, everybody. My name is Elijah Gracia. I've been working here at Royal Circuits in Hollister, California for about 6 years as an engineer. I did help design, or I guess edit your design so that it's actually manufacturable. That's about it.
Very good. All right. Greg Zeraldo. Yes, ladies and gentlemen, we've got that. Greg Zeraldo.
I think there's only one.
I know.
Literally.
You've probably seen the movie. Maybe you've read the book. Some of you have even eaten the Greg Zeraldo sandwich over at the pub next door. We've got him here, folks. Greg, tell us a little bit about yourself.
Good morning, everybody. Afternoon, depending on what time zone you're in. My name's Greg. I'm over operations with Advanced Assembly. I've been with the company now for coming up on 3 years. Spent the last 15 years prior to that working for a very large fabrication company in similar roles, designing very high technology, high layer count, HDI bare fab for military weapons and defense. So
Very
good to be
good.
here. Thanks.
Thank you, Greg. And Sebastian Weber. He used to be process engineer, but now he's process engineer level 2 from Advanced Assembly. Sebastian, tell us a little bit about yourself, you masked man.
Yes, I like to keep everything covered as much as possible. Mostly just to hide the hair. So I'm a process engineer for Advanced Assembly. I've worked here for about 6 years. Most of my job consists of just firefighting, usually design issues, and then feeding back a lot of that information back to the customer to try and help them figure out a better way to make their job more manufacturable, similar to what Elijah does, just on the assembly side.
All right. So before we get going, maybe we could do just very quickly the difference between fabrication and assembly, since we've got both parts of the business here today. What's the difference?
Everything.
All right. Now that we've cleared that up, let's
Chalk that up as one right.
Greg, you've worked both sides of the issue. What's the difference between fabrication and assembly for our listeners?
Fabrication is taking your raw materials, your pre-preg, your copper clad laminates, and you're creating a bare board fabrication. Assembly is the actual act of placing components on that board that you fabricated.
All right. Well, with that, we've got a few questions preloaded, and we've already got a dozen or so in the Q&A. So let's start hitting them. The first one was emailed to us ahead of the webinar, and we had a customer who asked, what conductor and dielectric material should I use in my design? I was going to tag this one to John, who isn't able to join us today. So unless anybody objects, I'll be happy to field this one.
Sounds good.
Go for it. That's a pretty broad net to cast. So I think that there's obviously, it's application specific, but yeah, Mark, let's start and let's go from there.
Yeah. So what I was going to say is actually exactly what Greg did. we've got a lot of different materials available to us, and you're probably not going to know everything that we do or everything that our engineers do. So my advice is, back at the beginning of your design, once you have your schematic made, email our engineers. We've got 2 engineers dedicated exclusively to creating stack ups, impedance control, whatever you need. If you've got specific thermal properties, these guys spend 8 hours a day, 5 or 6 days a week, just going through data sheets, learning about the different materials. They can do this job so much quicker than you can, and better, because that's really all they do. And the best thing is that it's free. So write down these email addresses. If you have a rigid board, you can email Teresa. If you've got a flex, semi-flex, or a rigid flex, Omar, both of them work together all the time. But they just sit around figuring out what materials have what properties, and they will generate impedance controlled stack ups for you. And again, it's all free. If they have questions, if there's something that's really, really strange out there, we also have a great relationship with Chris Hunrath of Inselectro. The guy is just a walking encyclopedia of material science. So for the specific question that the person asked, what conductors and dielectrics should I use for my specific design, you're not going to know what all of these things are. This particular stack up that I pulled is made out of 370 HR. Well, what does that look like? Sorry. So this is 370 HR, and it's just referencing a specific glass and weave pattern. So you don't need to worry about what the weft and warp fabric profiles are, what the resin content is. You just need to tell them, I need X and X property, either specify it by a slash sheet or whatever, and let them go through and pick whatever material that it is. If your concern is cost, even all the better. They'll design for cost for you too. Anybody want to add anything to that?
Yeah, Mark, one of the things that, you and I have done over the last year is, discussing high current, high heat and everything like that within board fabrication. And I think this is a really good point to this too, is that, when you're asking about conductor and dielectric, your conductor width and spacing and your dielectric thickness and your z-axis is all going to be extremely important depending on what you're actually building. So, to kind of nod to what you and I have talked about for the last year, if you have an application that's going to see a constant run of high current, high heat, atmospheric pressures, if it's an aerospace payload, you're going to have to look at something that's going to be more robust. Obviously, all of those changes is going to affect how fast your board is too. So I think it's extremely important to really, first things first, and this is just, design 101, is really understanding what the true breadth of your application is before you, even at, the design stage, you need to design it to be, for its final form, even if you're looking at just a functionality product. So just some stuff to think about.
Absolutely. And when people ask what conductor should they use? Usually I would assume that they're asking, am I going to use rolled annealed versus electrodeposited foil, some of the thin stuff. But anyways, hit our experts. That's what they're there for, and they are free. Now, you just mentioned something, Greg, about trace and space. So this might be a good question for both you and Elijah. Question was, what's the minimum trace width that you guys can manufacture?
That all depends on your copper weight, but our smallest copper weight, which would be 1/4 ounce, we can go down to 3 mils of a trace. That's going to be a 3 mil trace, 2.5 space. Sorry.
So why those minimums? Are there any, are those really as low as you can go? Can you go a little lower? How did we come up with those numbers, Elijah?
Those, just through the years that I've been here, those numbers probably started around like 5 and 3 maybe. And they've just gotten lower and lower with every year that we continue to add more machines, more tanks to our process, and obviously more experience. We're just getting that number lower and lower. I think we're pretty close to getting 2.5 mil traces comfortably. We can do it. It takes a lot of time, takes a lot of babysitting, but we're getting there.
So I should design to these numbers?
No, these are our actual bare minimums for, I guess, after edge comp.
All right. So I should probably, if I can, then not do the actual process minimums if I can avoid it.
Absolutely. If you can go a little higher, go a little higher.
Okay. Greg, did you want to add anything to that about some of the dangers of thin traces with heavy copper?
Yeah, I mean, you asked the question, is that really the lowest you can go? And technically, obviously, no, it's not. But at the same time, the minimums that Elijah's establishing are industry minimums because that's where your safety net starts to disappear. Photoresist can only leave enough meat for you to be able to accurately etch something down to a certain space. I mean, yeah, you can go down to a 1 mil trace, but it's going to be over etched. It's going to be basically a piece of hair on your substrate. And unless that is being held by kid gloves, through the manufacturing floor, and what you're doing with it, it's going to be impossible to manufacture. There's no reliability in it. There's no repeatability in it. It's going to be kind of a stroke of luck that you've gotten that. So, most, for the commentary on that, when Elijah's, putting that out there, it's like, this is what we can repeat day in and day out. This is what our process has spoken to us and told us what we can do. Again, you can do anything under the sun. One, either you're going to pay for it because you're going to have guys like Elijah and people like Sebastian, process engineers, and upper level operators and technicians hand carrying a job through, which is exponentially adds cost to your build. So again, once again, to Elijah's point, if you don't need it, you don't need to be Superman and design the world's craziest and hardest board just because you feel like you have to.
All right. Thanks, Greg. Thanks, Elijah. Yeah. Sebastian, you were useless there.
Yep.
But
I got that pretty face, so.
I'm just messing with you, buddy.
And argue.
That was the funniest joke I've heard all year. All right. Next up.
Saying what everyone's thinking.
Is a question for Sebastian. This one actually came from a customer via email. And this I actually sent to you a few minutes beforehand so we could discuss it. But the question is, we've been having problems with SMT pads not being flat and the parts moving during reflow. The biggest problem is the small pads for quad flat pack and the fiducial for placement machine not being recognized. So that's our first question.
Yeah.
And we were discussing that maybe the customer here found the wrong root cause. Would you like to tell us what you were thinking?
Yeah, so I mean, there's a couple different reasons why parts would move during reflow. One of them is not following manufacturer recommended footprint. If you have, for example, if the pad is supposed to be a certain size and you design the pad on your board larger, during reflow, when that solder turns liquid, it's going to move that part around. Just based off of wherever the heat is and wherever that solder is most liquidy, and wherever it just really wants to flow. A couple of other things. The only other thing I could see was flatness for SMT pads doesn't really affect the assembly process except during paste in regards to stencils. So it could also be a stencil issue. Maybe the pads are being over etched and they're just depositing too much paste down. Maybe that extra paste is what's causing it to float around. But I think there's probably something else that's going on here. That's a bigger root cause. Maybe the boards that they have are just not the right design. Fiducial recognition shouldn't be an issue either. Most machines, you can just update the fiducials on it and just do it on the fly and continue going. So I'm kind of doubting that that's what's going on here. But if they could give more information, we could definitely do a deeper dive into it and try and figure out what's really going on.
Okay. But yeah, it's not likely that your pads aren't flat enough. One of the most non-planar finishes is hassle, and people use that all the time with no problem. So you might have a different root cause that you need to dig out. All right, and I did a little spelling correction for the next question. Are there any advantages or disadvantages of using immersion silver versus immersion gold? What would be the storage time for the boards? We order some boards 6 months in advance. Production is concerned about oxidation before the board is assembled. So it looks like we've got a process engineering question for fab and then one for assembly. Elijah, you want to tell us about some surface finishes?
Yeah, so silver immersion is going to oxidize a lot faster than ENIG is going to. ENIG is going to hold up a lot longer. Shelf life as far as silver immersion is about 6 months, where ENIG is about a year, actually longer than that, but most boards usually expire shorter. But silver immersion comes with kind of a gotcha where it has to be handled very carefully with gloves on, and they have to be wrapped individually with pieces of paper in between them so that anything that's touched, like they don't scrape each other. It's very fragile. So it is cheaper, but comes with some gotchas there.
All right. Sebastian, anything you'd like to add?
Yeah, and I mean, it's really dependent on how it's packaged, how it's stored, what kind of environment it's sitting around in for 6 months. I mean, if you're going to go the cheap route, I would go the cheap route, but in the correct time frame, and I would try and get those a lot closer to when you're trying to assemble, so you can reduce some of those variables that you don't want to deal with on the assembly side. There are methods for removing the tarnish on these. They're extremely costly, and they're probably going to outweigh whatever cost benefit you got from going with the cheaper finish. So I would still definitely recommend using the immersion gold, because it's just going to give you that better reliability and less of an issue especially if you're storing boards for longer than it should be stored for.
All right. Thanks, guys. Yeah, gold. Go ahead.
I was going to interject on that too, real quick. So, Elijah, you guys don't have immersion silver in-house, do you?
No, it's actually outsourced.
Yeah, and so and that was one of the topics that I wanted to bring, is that there are very, very few fab shops that actually keep an immersion silver line in-house. Usually that's out of like a specialty plating shop. And so, one, you're going to lose control of your lead time, because instead of a one-stop shop with it going right to Elijah, you're getting the entire fab done through ENIG, and in a box, basically. Your final finish is one of the last processes before the boards get routed out of the panel. And so you're going to add at least probably another 2 to 3 days, depending on the proximity of that plating shop to the fab house. So, if you're in a time crunch, immersion silver is not going to be conducive to what you're doing. And second of all, it makes it a lot more difficult to manage the process, because, there's expectations and flow downs that come from, the fab house to the third party plater. But at the end of the day, we all know with everything is that, when you sublet something out that you're not in control of, variances can occur that you can't always be prepared for. So it's just honest conversations with yourself and what you really need.
Yeah, and kind of add on that too. I think this was a question by the exact same person. So I think what the train of thought was, the flatness of the SMT pads was the issue, and there was like a talk about using an immersion silver and immersion gold to help reduce that. But once again, I don't think that the issue here is actually the flatness of the pads. I think there's something else that's going on.
Yeah, and I'm with you on that one. All right, speed round. How important is having copper pores on all layers to balance the board on a simple 4-layer 6 by 6 inch board?
Copper pores.
Okay, so what they're referring to is having and maintaining a balanced stack up. I've got another slide on that here. So the question is, how important is it to have a balanced stack up is the first thing. And then how important is it to maintain that stack up balance in your design? So as an example, copper pores from a designer standpoint is, see all this, like this green layer, it's all just a huge run of copper. Here we've got 4 copper pores in different colors, red, light green, green, and salmon colored. So these don't have to be here. I could have electrical connectivity without those big pores of copper, well, except for maybe the ground plane. So how important are these to keep the board from potato chipping during assembly?
They'd be very important. Basically, you want to balance stack up, because like you said, if it's not balanced when it gets to lamination, it's going to potato chip. It's going to warp. And some people are okay with a little bit of warpage. We do have a tolerance, but once you get to assembly, you're going to have a hard time trying to place those parts on.
Yeah, we don't like warpage.
Yeah.
How often does it happen?
Pasting, makes assembling. Typically when we get boards from the board house, typically we get our boards almost immediately. When we get boards that have been sitting around for a while, sometimes there can be some warpage that just occurs over time. Most of the time we don't see warpage until after the reflow process. And then it becomes more of a bigger issue. For example, we'll start building the first side and then we'll move on to the second side, and the second side now has warp, and that prevents us from being able to paste it correctly. It prevents us from being able to place things correctly. It just adds a whole nother dynamic to it. Not only that, once you start doing hardware or box build type stuff, you start putting a lot of mechanical stress on that board. Even though it's warped, you're going to start getting cracked solder joints. You're going to start having failures later on. It's not ideal. So I agree with Elijah. It's definitely important.
So add copper pores if you can. Obviously, if you're doing some high voltage, you've got to respect your creepage and clearance allowances, but the better balance, the better assembly is going to be, higher reliability your board's going to be at the end of the day. All right, next up is a easy one, and Elijah, this one's all yours. What is our standard panel size?
18 by 24 is the standard panel size, but we use the outside 1 inch all the way around. So you're going to get a usable 16 by 22.
And I could make a single board that's 16 by 22?
Yes.
Okay. What about when I'm doing panelization and I have to allow kerf for my route outs? What do you guys like for that?
Our standard is going 200 mils from board edge to board edge.
Okay. Next question, and I'm typing these out of the Q&A box. So if you guys see any that you want to jump on, please feel free to. But our next question is regarding circular boards, and I just lost it. I'd like recommendations about dealing with circular boards. Some of my designs are strobes for vision lighting so that the PCB is a donut shape. So any recommendations for dealing with round boards instead of rectangular ones?
I don't think there's, I mean, unless there's an actual, like, I mean, unless you're using like an exotic material or something like that, there's, I mean, a round diamond, I mean, you know, there's no real standard shape or standard profile outline anymore. I mean, you know, yeah, you see a board and you see a rectangular or a squarish board, but I mean, you know, there is, I mean, we see shapes and sizes all under, all different types, and it doesn't matter. Your biggest things are just like what we talked about as far as, you know, even stack ups, you know, things like that are going to be conducive to the fab and the assembly process. You know, the pick and place machine doesn't care what shape your board is. You know, a router doesn't care what shape your board is because it's routing to a program. You know, a reflow oven doesn't care what shape your board is. And maybe Sebastian, you can talk to that if you've seen any, you know, higher failures based on the shape of a board.
Yeah, so there are definitely some risks. I think the biggest risk that I typically see is during the coding phase. So whenever we take your data, we'll translate it into data that our machines can take. And one of the things that does get lost in translation is rotation. And especially on a round board where you have different things angled just at weird angles. The concern is that your package library might have a pin 1 orientation of like 90 degrees, whereas ours is 180. So it's always good to review any sort of engineering documentation that comes back mid-process just to make sure that the rotations are right whenever you see a circular board. Other than that, large circular boards have no issues. Really small ones, like the size of a quarter or something, you start to get issues with fiducials, just because it's hard to get that to line up correctly. But as long as it's well,
but that's just a dimensional size, not a profile outline, though, right? That's just because it's small, right?
Yeah.
Or is it actually, yeah?
Yeah. So it's that, and it's also just trying to line something up on. For example, our paste printer uses kind of the larger fiducials and smaller ones, so it runs the risk of not being able to see the small ones correctly, or if there's multiple things nearby that are very similar to it, it can sometimes get confused. Using fiducials that aren't circles or like squares on a circular board usually has a better, it helps improve manufacturing once we get down to that point. Other than that, yeah, it's very minimal problems. Normally, it's not something that stops the show. It's just something that we have to work around a little bit harder for, but nothing critical.
All right. Thank you so much. Next up, we've got any issues with placing parts on both sides of a HDI design? Are there any parts that you shouldn't put on the bottom, for example?
Yeah, so I guess one of the biggest things that I see on this is large thermal mass components or very, very heavy components that are likely to fall off during the reflow process are always a risk for putting on both sides, because you put it on one side, if no staking or adhesive is applied, then once you flip it over to that other side, there's a very good chance that it's going to fall off during reflow. The other issue is those large thermal mass parts. If you have like a large custom inductor or a large ceramic BGA or something like that, those are going to absorb heat and prevent or potentially prevent proper reflow. So it's important to just try and design them on one side. Obviously, there's a risk with that because you then have a large amount of thermal mass on one side and you can end up getting bow and twist. But sometimes it's just completely unavoidable.
All right. Thanks so much. Next question we've got for our friend Elijah, who's been quiet over there. We've got a few different questions about other manufacturing minimums. For example, what's our minimum annular ring? What's our minimum solder mask?
Minimum solder mask gap is going to be 4 mils. That's basically the smallest trace we can make out of solder mask. And the minimum gap between 2 pads. As far as annular rings, we like to keep it around 3 mils. That's a nice area. Yeah, that's about it. That's an easy one.
Okay, that didn't take too long. Can you, since we've got your attention, can you tell us a little bit about plating, how plating works? I was still typing this one up. We're getting a little ahead of me, but what's our standard plating thickness?
So standard plating thickness in the barrel is going to be 7/10 of a mil. That's standard. And then about the same on the outer layers.
Okay.
And then pretty often, I guess we're seeing it more now lately, is 1 mil in the hole. A lot of people are asking for that, which is going to be about 1.4 mils, or I'm sorry, 1 ounce in the hole, 1.4 mils. Occasionally we do get the request for 2 ounces in the barrel, and we comp your drill size to allow for that.
Okay, that was actually a question that somebody had as well. I'm looking for it, but I don't see it. But the question was, if I've got a board and I call out 100 different drill sizes, do you actually go out and find a drill of each side, or you just kind of get close?
If any of them are close enough, we'll get close within tolerance. I guess the industry standard is plus or minus 3 mils. So if we can find something like you have a 55.5 and you also have a 60 or 56.5, then yeah, we're obviously going to use the same drill size.
Okay. Next question for Greg and Elijah regarding copper weight. And the question is, can I use different copper weights on inner and outer layers?
Absolutely. As long as you follow that rule of having your balance stack up, if you cut it in half, you want the board to mirror with dielectric and copper. So as long as your stack up is balanced, yeah, there's no problem at all. We're not going to ask you any questions. Once we see something unbalanced, if you have 1 ounce on your first 2 layers and ½ ounce the rest, that's where we'll stop you and find a solution.
Greg, anything you'd like to add to that?
I think the only thing to that is, obviously, on the initial, the DFM, the design for manufacturing scrub, when they're looking at these things, is, there's going to be questions that are raised. Like if you have a stack up that's just not an even stack up, I mean, that happens all the time. People have uneven stack ups all the time, but it's just more of just a flag and saying, hey, look, you can expect X amount of bow once it comes through, your thermal cycling through the fab process, and there's going to be an X amount of bow and twist that you're going to see on the assembly side through thermal excursion. And so there's a lot of, designers who, if you have a high heat or high current ground plane on an interlayer, you're going to want to have, thicker copper to allow for that. But maybe you have, a lot of thin trace and space on the outer layers. So you're going to be running 1/2 ounce or 1/4 ounce copper. And that happens all the time. But, you just need to be prepared to understand that one, the CAM engineer up front is going to automatically flag it and say, hey, look, you have these things right here. They're a little discrepant. Do you want to proceed with this? And then knowing as the designer, that there's going to be potential risks on what that fab and what that assembly looks like long term. So, but yeah, long and short of it, yeah, of course it can be done.
All right. Thanks so much, guys. Next question, and I'm getting lazy here and just doing screen captures because I'm not keeping up with the typing, but it's regarding panelization. Is it more cost effective for the designer to do panelization or for the design shop to do panelization? I'll take a crack at it if nobody wants it.
Go for it.
I was going to say, let us do it. We've got software that automates it, so we're not putting a person on it and devoting man hours to this. We just feed it into a program, floats them out. One of the big problems with having engineers do their own panelization is the reference designators. You end up with duplicates all over the place. It becomes just a huge headache. So if you can, just say, hey, I've got this board. You guys want to panelize it for me? Let us panelize it for you. That would be my opinion.
Oh, I can 100% agree with that. A lot of times, also the definition of panels and boards sometimes gets confusing. A customer will come to us and say, hey, I need 5 of these boards built, but really it's 5 panels of boards. And then we get to the floor and there's confusion on whether or not we're building 5 single boards or if we're building 5 panel boards, and then depaneling those into 25 or whatever it is, individual boards.
Okay. Greg, next one up is for you because you are our heavy copper expert. The question is a little malformed, so I'm just going to rephrase it. But the gentleman wanted to know what copper weight they can use to carry, what copper weight carries what current.
Yeah, well, I think, off the top of my head, I'm not going to be able to spit a whole lot of data back out. But I mean, as far as what you just put up, the chart that we've been using for, our webinars and talks over the last year or so, it's got a really, simple gauge. So, if you're looking at the slide right now, you have your darker blue that represents 1/4 ounce, go up to 1/2 ounce, go up to 1 ounce in green, 2 ounces red, and then 4 ounces with this more purplish color. And so by looking at this chart, if you have a trace width of 5 mils, you're going to, in your y-axis, you're going to look over there and you can go across X and just start to see where these start to align with as far as copper weight goes. If it's, your trace width is not going to work, or could be potentially not working at 1 ounce copper. It's not going to work at 2 ounce or 4 ounce copper. As you get higher in trace width, you start to see where your copper weight and then your current down here at the bottom is going to align with. So it's just a rule of thumb, simple as, heavy copper needs to have high current. There's no point in putting anything that's low voltage, low current. Is there anything less than or anything more than 1 ounce copper? Again, it's just designing just to design at that point.
Yeah. I would also add that if you go and use an online trace width calculator, unless things have changed, they're just universally wrong. They're using some outdated data based on IPC 2221 that was replaced, 5-6 years ago by IPC 2152 standards. If you want to look more into it, we've actually got some blogs up at our website that discuss using heavy copper in your designs. And we've got charts for just a variety of allowable delta T's that let you get a good idea of, what an appreciable copper current versus trace width is. And Greg's got a whole webinar over at our blog. So if you want to, let me see if I can get back to this slide. And I will link back to our blog and just go there or shoot me an email and we'll take a look at it for you. Sound good? So very simply, blog, aapcb.blog, and look for a webinar. It's probably 2 or 3 pages in from Greg Zeraldo. Sound good? Okay. Next up, we've got a question regarding solder mask weight. Does the solder mask cover equally over the metallized surfaces and the non-metallized surfaces? Is it the same thickness once it's applied?
Elijah, you want to start with that, or you want me to?
Go for it. Looked like you had something to say.
Well, I mean, to the point. I mean, if we're looking at a metallized surface on a board, that means it's already been etched, right? So it's going to have a topography on it. So the way that it is going to have, obviously on your non-metallized surface, just your dielectric, your substrate, basically, it's not going to adhere to it any differently or anything like that, unless there's a cleanliness issue. But, the higher or thicker your copper weight is, the thinner your mask is going to be at the peak of that copper. And Elijah, I'm sure you guys have seen this before too, where, it appears that there might even be missing mask, but it's actually in fact covered and encapsulated. It's just very thin mask. And so you start to see a little bit of that pink copper start to shine through a little bit. But when in fact there is coverage and it is acceptable by IPC. Hopefully that answers the question a little bit, but I mean, as far as adhesion and coverage and thickness and stuff, I mean, side by side, they're the same, but an etch board is obviously going to show topography. If you were to get like a Z-axis grind on it, it's going to look, like railroad tracks, basically, all through the board. And so your higher tracks is going to be thinner mask and vice versa.
Yeah. And from the fab point of view, this is all done. You have to remember it's being done with a squeegee, basically. So stop and think about, if you have uneven surfaces and you're trying to squeegee some paint, what's going to actually happen. And even in the small period of time we dabbled with spray on, you get the same thing because it has to sit at an angle when it dries. So it does tend to drip and you're going to get that same, some gaps get filled more than the others kind of thing.
Okay, next up is a series of questions that we're probably going to have to punt on to a certain degree since we don't have John here, but I'll take a stab at them as much as possible. So the questions are, can I use solid copper planes on flex PCBs in order to have better impedance stability? What are the pros and cons? And what are your recommendations for hatching parameters for flex PCB? Would anybody like to jump on these, or do you guys want me to take a stab at them?
Take a stab, Mark.
Okay. I'm on it, Craig. I'm on it. All I need is an order and a direction, and I'm going. All right. So what you're going to want to do is talk to somebody else. No, I'm kidding. But really, we've got a whole Flex PCB shop. We just don't have anybody on from the Flex PCB shop today. But if you want to shoot us an email, or shoot me an email, I'd be happy to connect you with the right people. And my email is mhughes@aapcb.com. And then I'm not going to punt completely. I will tell you what I do know. It's not MJ Hughes, it's just M Hughes. So shoot me an email and I will connect you with the right person. All right, the trouble with using the copper plane isn't necessarily the copper plane. It's what happens when you've got your trace and the copper plane stacked on one of the other. And what you've effectively created is an I-beam or a T-beam. And that really reduces your bend radius. So that's the issue that comes into play. Now, it depends on how you're designing this. Is this going to be a one-time bend panel? Is this going to be something that's going to be flexing over and over and over and over again? So really, from a design standpoint, you're going to want to use a hatched ground plane. Now, there's some resources I can direct you to. Some research has been done as what you want the ground plane to look like. Do you want it just to be crosses, X's, or is it better just to cut out holes? So basically fillet all of those X's. So again, shoot me an email and we can better follow up with that one than trying to guess on, well, we're being recorded and I would look silly on the internet and then somebody would correct me. Email me. All right. Next up, we've got on the assembly side, do we do consignment?
Yes, we do. Yeah, so I mean, we'll pretty much take we'll do full turnkey or consignment. If you have some custom parts or some parts that literally don't exist anywhere else on the planet except for in your shop, you just got to let us know what parts you'll be supplying, and then we can set that all up so that we know what's going on. We'll also typically create some just labels for you. And labeling those parts, especially if it's custom or a non-standard part number, can help our receiving team better identify and just reduce the amount of questions that we end up having to ask you once we start looking through your kit.
Do we like consignment?
I don't think it's that I don't think it's that we don't like it per se. I mean, we work with, vertical markets in every industry. And so, there's a lot of people that love what we do for turnkey. And then to Sebastian's point, there's, people who have custom parts, there's custom programming in their parts. And so there's an inventory that they keep that they absolutely must use. I think the only downside to the consignment part of it is that, again, to his point with the labeling, if the labels are not properly used, an internal and a non-industry accepted part number that is used by a customer can make it very difficult to ID what's been received in the box that's been shipped from the customer. So it ultimately creates delays and potential holds in our system on getting the assembly process started because we frankly don't know what the part is. If there's an industry accepted Googleable part number, and on the bag that we receive it says MF12345, that doesn't mean anything to us, and especially if it doesn't correlate to anything on a BOM, we have no idea what it is. So it's certainly doable. We do it all the time, but doing it right is key.
Yeah, doing it quick is difficult. That being said, of course, if you do use the labels, it's a lot easier. It's a lot simpler. Everyone is well aware of what it is, and it reduces the risk because obviously your parts better than we do of something getting mixed up. The only other concern with consignment parts is if they've been sitting around for a long time or there's a concern about moisture potentially being an issue, those parts probably would need to be baked. I think there was a good example. We had a customer come in with parts that were originally manufactured in 1997. And whenever we reflowed them the first time, because we were unaware that they were that old, they just totally popped and exploded. So then we had to pre-bake those parts, and after we pre-baked them, they came out just fine. But it's a good example of making sure that you're aware of what kind of environment your parts and your boards and everything else is being stored in, so that you can properly feed that information to the assembly house so they can prepare and make sure that they're not missing out on something.
Yeah. Something else I would bring up too is that Advanced Assembly is a top 10 buyer for all of the major part suppliers, DigiKey, Mouser, Arrow. We're number 6 or 7 on their list of clients, right? We are way up there with our volume. So we get stuff same day, next day. We know that it's ESD controlled. We know that it's climate controlled, right? We know that these parts are going to work out just fine versus something that maybe has been sitting around in your garage and gets shipped to us. Maybe it's been zapped. I don't know. Not everybody's as careful about ESD as they should be. You don't know. So as a designer, I like to remove variables whenever I can. So I'll pay the extra, 2 cents to buy a new resistor rather than reusing one I had from 3 years ago. So that's just me. All right. So we do consign parts, do it every day. Got a whole team that does it. All right, Sebastian, how close can I put my parts to the board edge?
This is always a topic for discussion. I mean, you can put them as close as you want, but the closer those parts get to the board edge, the higher the risk for damage during any sort of handling, either during the assembly process or the shipping or anything else after that. So, I mean, as far as being able to assemble, there's all kinds of jigs and fixtures and custom things that we can make in order to place the parts on the board on the assembly side, but there's no big requirement. It's just the closer you get, the more likely it is that your job might take a little longer than normal jobs.
Hey, thank you so much. Next question. Sorry, I was trying to get ahead again, and I'm not that talented. Who is my first contact? Who do I talk to whenever I have a question anywhere along this design?
Yeah, so I mean, I get emails all the time from different customers that have some sort of question. A lot of times they'll go through like our sales reps or something like that. So I always encourage them to go through the sales rep, just so the sales rep can kind of be in the loop too for whenever a new job comes through. But yeah, you can always reach out to pretty much any one of us. I think here is experts in being able to provide some of that feedback to make a design more manufacturable.
So the emails are your salespeople. The other nice thing about contacting sales is it then becomes their responsibility to follow up. The people that we have on the call right now are working the line all day, every day. They're busy people. And it's easy to say, oh, hey, I'll get back to that. And then 20 things come at you and you forget to come back to it. So if you hit sales first, they can handle it. And it's free. The engineering services that we offer are free, right? You don't have to buy anything. Just ask, and we'll try to get that handled for you.
Those salespeople keep us honest.
Me too. All right. Question is blind vias, Elijah's favorite topic.
Ew.
I have a question about a 4-layer with blind via expense with the power and ground plane in the center layers. The price becomes prohibitive even for a 20 by 20 board. Why? What should I do instead? Okay, I've got a question here. A blind, I'm thinking buried via. What could they do instead, Elijah, other than just do through holes, which is the absolute cheapest way to go?
Yeah, obviously, if we can go through holes, that's great. If not, the best next thing would be to try to, I guess, lessen the amount of blind vias that you're doing. That's the first thing we'll try to do. If you've got multiple blinds going through multiple different stacks, that's going to be more lamination cycles. Obviously, more money for that. And so first thing we're going to do is try to lower the amount of lam cycles you got going on.
Okay, so why are blind vias so expensive? Maybe you could tell us quickly how a board is made.
So basically, we have to start with the center of the sandwich. Then we add the next outer layers from that. And we're going to have to laser drill and then copper fill, plane it, then image it. Now we're going to make the next layer and do the exact same thing over and over again, depending on how many stacks you have in your blinds.
Okay. Anything else you want to add, Greg, from your years of experience over at the other company?
Yeah, I mean, to his point, I mean, it's just like you're making a new panel every time. You're making, a panel of a panel of a panel of a panel just to make one complete sandwich. And so you have like this, giant, turkey and cheese sandwich, but at the end of the day, it's only one sandwich. It's just a lot of layers to it that, that necessarily don't need to be. So if, the technology that you're designing requires that, then that's different. But the question that you're putting up on there is regarding a 4-layer with blind vias. A 4-layer with blind vias, unless you're having like micro via, from 1 to 2, which would basically just be one sheet of material, and then you have your layer 2 and 3, which is going to be a core, and then your layer 4, which is going to be another piece of material. It just sounds like, just from a design standpoint, that's incredibly difficult to do in the first place. So, it just comes with the territory. I mean, as soon as you start adding lamination cycles, it's just where it goes. Laser drilling and copper filling. Copper filling is extremely painful to do. It's extremely difficult to do, to get your entire, via encapsulated, so there's no voiding in it. As soon as you get voids in it, it's done. So obviously the cost is going to go up because the yield is going to be nowhere near what a standard 4-layer with through hole is going to be. So that's where your cost driving is coming from.
All right. Thanks so much. And then I will add, from a design standpoint, pick a different layout, man. A 4-layer with power and ground on the middle is what everybody is initially taught in school. And depending on how your board is made, if it's a cap construction, you could have horrible coupling to your ground layers. I mean, your top layer, if you're drilling a blind via down to ground, the distances in a a 1.6 millimeter stack up, I mean, you're looking at like 48 mils versus if you just coupled down to the next layer down, it's only 8 mils. So if you can do a mixed power and signal layer and use your layers 2 and 3 as ground, you're going to have much tighter coupling, a much better design from an EMI standpoint. You probably won't need the blind vias because anything that you're doing to connect these, you're going to be connecting through hole vias from the top layer to the bottom layer. So you're eliminating blind. There's no buried. Do everything with through hole vias and change your layout. Rick Hartley has presentation after presentation on using a layout similar to this one, or it doesn't have to be this one. It could be something else, but change your layout, change your board stack. It's going to require you to change how, your traces. Yeah. But you'll have much better power integrity, much better signal integrity. That would be my advice. All right.
Cheaper cost.
Yeah, much cheaper. While I'm pulling up our next question, Elijah, you want to tell your story real quick about your elimination of a single blind via and what that did to customer cost?
Yeah, we actually had just finished a webinar and somebody had emailed us asking about their design, what we could do to change it. And it went from blind via. Right away, we were able to convince them to swap over to an epoxy via fill. And they still weren't too happy with the price because it was a pretty high quantity order. So then we knocked them down to just a single through hole. And it actually ended up saving them close to like $50,000. And that took maybe a day or two.
Yeah,
out
you
of their
cranked
design.
that out pretty quick.
Yeah, our team's amazing at being able to help out customers figure out stuff like that. And I mean, $50,000, they could have at least sent me like a Subway gift card at the least.
Taking you to
All this talk of sandwich and chips.
Yeah, Taco Tuesday, get you something. So, okay. So a couple other quick questions. Next up, we have, can somebody tell me what a flying probe test does?
Yeah, I'll take this one. So a flying probe test is basically like a box with a bunch of like tens and hundreds potentially of probes that just come down and poke your board extremely rapidly to just test for different signals. Mostly it's looking for like open, shorts, the really obvious ones, but it can also, a lot of the more advanced ones can also do different measurements. So if you have the right files and everything else like that, we can actually compare the board to that, or we can do just an overall yield test where it just takes all the boards, you program a golden board, and then it makes sure that all those boards fall within whatever those parameters are.
All right, and I think you're conflating flying probe with test fixturing. The flying probe usually just has the really quick moving tests. It's a non-fixtured thing, so you can adapt it to any board quickly versus the fixture tests where you have to know where the test points are and all that.
I think he's also Sebastian's talking about assembly flying probe.
So,
okay.
So even the assembly,
yeah.
The assembly flying probes have multiple probes that can also poke down. Like you can do, obviously they have the single 2 points or whatever that can move to different locations, but they have some of the more advanced machines that have multiple probes that can be testing at the same time.
Yeah.
Or at least not testing at the same time, but coming down at the same time.
And for fabrication, it's 2 probes on each side. They're kind of doing the same thing, but one board at a time. Again, just checking for shorts and opens based on the program that we gave it.
All right. Can we do back drilling for high-speed designs? Elijah?
Sorry, I was reading the question. Yeah, absolutely we can. Back drilling, it's again a pretty tedious process we got to go back and do, but absolutely.
Okay. We're just going to take 2 more and then I'm going to let you guys get back to work. Next one is going back to our circular or odd shaped boards. Would it be beneficial to have some rectangular breakouts on these things for alignment and fixturing and whatnot?
I mean, that does help. It doesn't hurt. It just adds an extra step. Of course, we'd have to depanel and knock those things out. But it certainly doesn't hurt. It could increase your turn time. It could potentially increase cost, but that's just about the only risk you're looking at. Like I said, most of the time with circular boards, the actual risk for having them is pretty minimal, and we can usually work around whatever comes through, assuming it's not the size of a dime. So it's probably worth, or it's probably more cost in the long end to try and add something to it than to just leave it as is. Of course, the better thing I think you probably should do is just go and ask the assembly house, hey, can you guys do this? Or what do you guys need to do this as quickly and efficiently as possible?
All right. Next question is one that I will give to you, and then I can add from a design perspective anything that might be useful. But what are the advantages and disadvantages of filling unused areas on a signal plane with copper? This is our copper pour question, asked a slightly different way.
So it's asking for basically like non-functional copper to stay on the signal layer?
I believe so.
It just depends on what the, like, for me, in my experience, it depends on what the stack up is. I mean, if you have something that is, very light copper weight, you might want to keep it there. Or let me back up. If you're using light copper weight and really light material thickness, like a very, very thin material, it's like a high speed material, you want to keep that copper on there, maybe in like a webbing format or like a crosshatch format to keep like the actual like integrity of the material itself. But I mean, other than that, I mean, it's just residual copper that's left over. Some people call them non-functional pads or non-functional, lands and stuff like that. There's some, in aerospace, there's some primes that absolutely want to keep those non-functional parts there, just for whatever reason. And then there's some primes out there that absolutely want all that stuff removed off the Gerber artwork. And so it's really kind of personal preference, but I will say that on very light copper weight and extremely thin material that tears very easily, that's not going to hold up well when you're going to booking it through lamination and stuff like that. It's best to keep that stuff there if you can.
Absolutely. If it's helping you to balance your stack up, it can help prevent warpage. Copper doesn't expand much when heated, or at least not nearly as much as the dielectric materials that it's attached to. So it can constrain movement. Greg was also telling you, if you put some vias through this stuff, it can also help hold your board together. It can help keeping the copper from peeling. Disadvantages, though, you have to be careful. As Dr. Eric Bogatin says, there's two types of electrical engineers: those that design antennas and those that don't know they design antennas. So if you have this copper and it's not tied to anything, I'm sorry, I just realized I don't have the right slide up here for the question. If you don't have that copper tied to anything, it can become a radiator, an unintentional radiator, and destroy your signal integrity. So just watch out. All right, with that, I would very much like to thank everybody who asked questions today. If you have any follow-ups, please feel free to email me. I did skip some of the very, very specific ones regarding specific materials, because that would require us to research, and we can't do that in a live setting. But this was our first one. How do you think it went, guys?
Good.
I think it was good. Yeah.
Do it again tomorrow.
Hey, why not? Next week, we're going to talk all about panelization. So if you want to continue our Tech Teach Talk Thursdays, please visit us next Thursday at 11 Pacific. We'll be happy to talk to you. I'd like to thank Greg Zeraldo. That's right, that Greg Zeraldo, Sebastian Weber, and Elijah Gracia for all of their help and just wonderful expertise. I am going to make a correction because I keep misspelling my email. If you have anything for follow-up, please hit me at mhughes@aapcb.com. If you have any specific questions as you design, feel free to reach out to any of these gentlemen, or better yet, talk to sales@aapcb.com or sales@royalcircuits.com. Anything you guys would like to say as we get out of here?
Thanks for being such a gracious host, Mark. You did a good job.
Awesome job.
If
Send you some cookies.
I appreciate it, because I just keep hoping that if I keep doing a good job, eventually somebody will decide to pay me. I mean, I don't know. How long
I
did you
said I
guys
was
have,
going to give you cookies.
how long did you guys have to wait before they started paying you? I've been here like a year now.
Still
Is that
waiting.
not long enough? Okay. I'll do a maybe at my first performance review. I don't know. Anyways. All right, everyone. Thank you so much for your time. We hope to see you next Thursday. Have a great day.